Okay, so where were we? Yeah. Uh, Good evening. Today I'll be talking about Blenderbot Free, a deployed conversational agent that continually learns to responsibly engage. It's a chatbot. It's a social chatbot that's built by Facebook, or Meta as they call themselves nowadays. And so basically, it's interesting in that it's actually based on a large language model. And what that means is that they have taken a lot of training data from all around the internet, and they have used that to train a very, very, very large 175 parameter model, which was initialized from OPT 175 billion, and they fine-tuned it for a dialogue task. And basically what that essentially means is that you have a very, very large machine learning model that has been trained with a very, very large data set, which then theoretically it would do well in a variety of dialogue of natural language processing tasks, because it has learned some features about, the languages that humans use from all that data it has been trained with, and here it has been fine-tuned for a chatbot, a conversational chatbot. So it is deployed on the internet. Anyone can go to Blenderbot website and use it and talk with it. It continuously learns. So as you talk to it, as more people talk to it, it gets better. It tries to be responsible in its conversations. So in the past, there was this chatbot on Twitter called Tay, deployed by Amazon. By Microsoft, and Tay, right? You had a lot of people who tried to get Tay to say stupid things by saying stupid things to Tay, and because of the malicious inputs from users, you had Tay saying stuff like advocating for Hitler, or saying that Hitler did nothing wrong, and other racist things, which wasn't good. So Blenderbot has mechanisms to remain responsible in its utterances, and it is a modular system with a single transformer model, which is this 175 parameter model, which executes different modules based on input context. And we'll get onto what that means later, but essentially, to successfully hold a conversation with a human being, you kind of need to perform a variety of tasks. And so your model has to be fine-tuned for these tasks. So what are these modules? You have an internet search decision. And basically this, Blenderbot, it has two main sources of information. It has the internet. It has its long-term memory. So the internet search decision is basically a binary decision saying whether you want to search or whether you do not want to search. And generate internet search query is basically whether it is to generate a search query given the context, so that it kind of knows what the context of the conversation is, and it can search the internet appropriately. Internet search, well, is basically to take that search query and return a number of documents. And you have the knowledge response, which is that you want to have the context in the retrieved docs and to have a sequence on which you can ground the final response, and so on and so forth. But essentially, there is also a long-term memory and also decision on whether you want to access the long-term memory. Well, also access memory, this module, and to generate a response at the end. So the entire thing looks like this. So the person says to the bot, hey, who is your favorite F1 driver? So now the bot has to make two decisions in parallel. In fact, it has to make a decision whether it wants to do an internet search and whether it wants to do a long-term memory access. So let's look at the internet search decision first. So here it makes a decision whether it wants to search or whether it does not want to search. So if it does a search, then it generates a search query called F1 drivers. And so F1 drivers, you know, it goes to Google or some other search engine. It uses this, it uses a different search engine than we are normally used to, but you know, it's still just a search engine. So the search engine returns some documents, and from that it generates a knowledge response from those documents. Like here, you get stuff like Hamilton, Verstappen, and Vettel. And then, you have the long-term memory access decision, which is whether you want to access memory or not. And if it does access memory, it would recall that, and person 2 is basically the chatbot. So person 1 is the user, person 2 is the chatbot. And it remembered that on a previous turn, it told the person, which is the user, I'm from the UK. So that memory was so of course this is to ensure that the chatbot has a consistent persona. Like if in the middle of talking to a chatbot, you don't want it to begin by saying it's from the UK and end up saying that it's from Germany or Brazil, because that's not very consistent. So that's that's the reason why it has a memory store. And here it says that it has 3 entries in the memory store. Firstly, it's from the UK. Secondly, I love dogs. And the third piece of information is about the user. So it knows that the user is a hairstylist. Okay, so now it knows it's from the UK, and it knows the names of a few F1 drivers. It does an aggregation. After the aggregation, it generates a dialog response. So it comes out as Lewis Hamilton is my favorite driver. How about you? Who is your favorite driver? So in this case, it aggregated, the interesting fact and the external knowledge with the previous topic and something it knows about itself, like the personal fact. And it's, it decided to talk about, say that its favorite driver is a British driver, Lewis Hamilton. So that's how it kind of generates the response based on an internet search and a search of the memory. And now after that, it goes back to a user, and now it has to generate a long-term memory that, Lewis Hamilton is my favorite driver. Okay, so that's basically the execution flow of the Blenderbot free. Of course, in a case that no internet search is done and no LTM is done, then what it happens is that it extracts a relevant entity like a previous topic of a driver, and it goes into the aggregation as well. So, and then it tries to, maybe it can go into a language model and see what it can find. But basically, so it has a safety mechanism. And how they build that safety mechanism is that while it's deployed online, you have some training data, and that they use that to, and it has some baked-in safety recovery like mechanism. So when the user sends in a message, it goes into this sensitive topics classifier and offensive language filters classifier that's been trained on known examples of offensive language and sensitive topics. So it goes in, and user message goes in, and it go and they decide whether it's safe. As in, it probably doesn't, like if the user says like do you like football, it's probably a safe question. But if the question is like do you hate people of a particular race, that would probably be an unsafe question. So in that case, it would switch to a can response. So so even though the language model itself, Blenderbot 375 billion, it has a baked-in safety recovery. The bot response is also sent into the safety filter to decide if it's safe, just in case that the bot says something stupid it shouldn't have said. And if it's safe, if the user message is safe and the bot response is safe, it keeps the bot response and the chat continues. Otherwise, it switches to the can response. And of course, you have some offline processing that is for, it's not, doesn't affect the user directly, but they have, they do detect adversarial use, and they save examples for the study, for the training set. So adversarial use would be when a user engages with the machine, like without in a way that is not in good faith. So you basically have a user who's uncooperative. He doesn't want to keep the conversation going along. He just wants to say stupid stuff. And yeah, so that's an example of adversarial use. So this is basically an overview of the safety mechanism of Blenderbot. Now you have training data. So you have a lot of openly available data sets on the internet that have been developed by other researchers. And the Facebook team actually used these to actually train some of the training modules, some of the modules that we talked about earlier. And they come up with different ways to fine-tune different modules. So for instance, with the internet.
This is a reminder. SMS meeting.
Sorry.
Okay, here's Avatar, the Way of Water theme.
Alexa, you have to stop. Okay, it's my, and sometimes Alexa gets a bit excited if yeah, if you leave it with an alarm, or if it hears the name Alexa. Ooh. Sorry. But Where was I? Yeah, so different modules are fine-tuned in a different way. So for instance, in the internet search decision, it's just basically a binary classifier that's been trained on datasets with training dialogues containing human labels essentially as to whether you need to search the internet. They engage in this method called visit of Oz. So you get two people to talk to one another on a chat interface, but pretend that one of them is a chatbot and one of them is a user. And the guy who plays the chatbot would annotate that at a certain turn, in order to generate what he said, he actually searched the internet. So that kind of is training data for determining whether or not it is necessary to do an internet search. And for the internet search query, you have human-generated search queries. So you have a dialogue and you have a context of the dialogue, and the human basically says that after labeling that, I needed to consult the internet to generate my response to other user. In addition, they also told the researchers essentially what their query was, and that was used to fine-tune the generation of the internet search query. And yeah, so those are examples of the methodology of how they did everything. But essentially they found that Blenderbot 3 is well, it may not be as consistent as Blenderbot 1 and 2, but it is less factual, less incorrect, and yeah, and it has more good responses with a higher rating, and it has less error breakdowns, which is good. And if you don't mind, I'm just going to go on to the demonstration. So at this point, are there any questions about how Blenderbot? Yeah, so I haven't gone very deep into it, but are there any questions about how Blenderbot works? Okay, but basically this is Blenderbot. It's a cute face here, and it follows your mouse, the eyes. So what it says here is, welcome to Meta AIs, and of course, Facebook calls itself Meta now. Demo of our conversational AI. The AI is playing the role of a character that can converse on nearly any topic. Get to know them. This early prototype needs your help, blah, 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 blah. So let's just go ahead and start chat. And you have to agree to these things. All right, so let's chat. The AI is playing the role of character, and now it generates, the prompt. Hey, I'm happy to chat about anything. What's on your mind? And here you notice that the user actually can rate whether you think it's a good thing the bot said or a bad thing the bot said. So this kind of further helps them fine-tune how they should train. It helps the model basically continuously improve. So hi, I'm in a seminar right now with the Singapore Microcomputer Society. And let's see what it says. It's taking a bit of time. Cool. I work at a library, and we have a lot of books on computers and technology. So what do you do for fun? So let's see why the AI wrote this. So basically, they made a decision to search, and they searched for microcomputer society, but they didn't, they got something like computers have been used to coordinate information from multiple locations since 1950s. The US military SAGE system was the first large-scale and they didn't use but basically they chose not to access memory, but they basically found something generic about computers, so they talked about, so it decided to say that it works at a library. And since it's the bot has said that it works at the library, if you see the memory, now what the AI remembers about me is that I am in a seminar, and the AI's persona is that I work at a library. So it remembers this, and it, to ensure that the conversation stays consistent. What do I do for fun? So let's say I like to play tennis. Do you play competitively or just for fun? If so, where? Wimbledon? Just for fun in my school. Okay, so I play singles. Singles. Wow, I can talk to you. I'm talking to you right now. And how I should. So you see, now we have a breakdown. So this is an example of, like how Blenderbot has failed. And the reason why it has failed is because it asks me, how was your day today at the library? And, I never told it that I'm at a library. In fact, Blenderbot itself told me that the bot works at the library, but I'm not in a library, and that should not have been part of the memory. But somehow the bot thinks that I was in the library. So something failed. I wasn't at the library. And let's see how it responds.
Blenderbot is say US only at this moment.
Okay, I'm sorry. So, but okay, so oops. You can use a VPN to get in. I guess it might fall foul of like export regulations, because the US is very sensitive about exporting technologies. Exporting. Anyhow. Okay, right. Sorry, forgot what we were chatting about tennis earlier. What did you do today then? If not, go to a library. So let's try to become an adversarial user. and say, I was talking to you. Exercise. Okay, so it's starting to ask me very tennis specific questions. And so let's look at all the So what it now remembers about me is that specifically I was not at the library. So at initially, I think it asked me whether I enjoyed, the day at the library. I think because that may have been output of its language model. So yeah, so it did not use any memory and it did not search. So basically, the language model thought I was at the library based on the context, but it kind of forgot that it was the bot itself that said it was at the library. I was never at the library. So this is an interesting failure of the bot. And so right now, it's even with so much training data, 175 billion parameters, you still get embarrassing failures like this one, which is good. Like, it's developing, and from this conversation itself, the bot is learning, and that's about it really. But so right now we have two ways of moving ahead. Like, we can talk about something that Google is doing, or we can play around with the demo a bit more, depending on what is more interesting. Okay, let's talk about one more system. I like to talk about these things. Okay, now, so let's see. Okay. Okay, so the next thing I'm going to talk about is Lambda. It's very new. In fact, the paper just came out this year, and it's by this team at Google Research. So what Lambda is, it is a family of transformer-based neural language models specialized for dialogue. So in a way, it is similar to Blenderbot in that Blenderbot is also a transformer-based, a family of transformer-based neural language models for dialogue. But so like Blenderbot, Blenderbot has the 3 billion parameter variety and the 175 billion parameter variety. Here in Lambda, you have like a range of model sizes. from 2 billion parameters to 137 billion parameters. And these have been trained on 1.56 trillion words of unlabeled text. So that's a really large data set. Now, so why use a large language model in dialogue? So basically, they are able to represent long-term dependencies in text, and they're well suited for model scaling. And but of course, you know, you have various considerations when you want to build a dialogue system, and you know, one of them is naturally quality. You want to have a dialogue that is of good quality. You want a dialogue to be interesting for the user, something that can engage them, and so on. So you want quality in the dialogue, but you also want safety, which is what the Facebook team considered as well, safety, and groundedness. So groundedness in that you want the utterances of the dialogue to, you know, you don't want it to simply sound plausible. So for instance, something that sounds plausible but is not true is like, oh, the sun rises in the west and it sets in the east. So it sounds perfectly plausible. It could be something that a human says. And if the bot said that, you know, it's a plausible utterance, but it is simply untrue. So this is something important that the authors feel is important. Now, okay, so yeah, so they did some pre-training with the 1.56 trillion words in the corpus, and basically it's pre-trained to predict the next token. And they use like public web documents in addition to public dialogue data. So those, you know, that data makes up the 1.56 trillion words. And it's a decoder-only transformer language model with 64 layers. And so it has three metrics. Basically, we start with quality. And quality score has three components: sensibleness, specificity, and interestingness. So sensibleness measures whether a model's responses make sense in context. So you don't like if for instance the user says, "What sort of food do you like?" and the bot replies, you know, "Oh, I like to watch football games." That's probably not a very sensible response, you know, to the context that the user has created. And specificity. So it measures whether a response is specific to a given context. So let's say the user says, you know, "I like soccer." Sorry, need to sorry. A bit of the morning blues of having just woken up. But yeah, so specificity. Let's say the user says, "I like soccer." And you know, if the bot says something like "uh-huh" or "I see," well, it makes sense. It's a sensible response, but it's not very specific to the context. Like, you know, if the bot says "I see" or "uh-huh," that is something the bot could say in response to a very wide variety of user utterances. You know, you can say like, "Oh, I like laksa." And "I see" would also be sensible. So So you want to, in order to have a high quality dialogue, you want the dialogue to be specific to what the user wants to say. Otherwise, it won't be a very interesting conversation for the user. And interestingness is a less objective. It's a more subjective measure, and it measures whether utterance is likely to catch someone's attention or arouse their curiosity, or if it is unexpected, whether it is witty or insightful. And now safety basically is the need to ensure that the model's responses are consistent with human values, such as preventing harmful suggestions and unfair bias. So if, for instance, if the user tells the bot, Lambda, I'm feeling depressed, you probably don't want the bot to say something like, if you're depressed, it's better that you kill yourself, because that would be encouraging the user to commit suicide. But yeah, so it wants to avoid unintended results that create risks of harm, avoid unjust impacts on people, particularly those with sensitive characteristics. You know how the US is nowadays. And to avoid propagating or reinforcing misinformation that creates a risk of harm, or opinions likely to incite strong disagreement. So you do not want to say anything controversial. And then lastly, you have groundedness. So they strive to ensure that Lambda produces responses that can be associated with known sources. The output from a language model should not only be plausible, but also correct. So here, groundedness is the percentage of responses containing claims about the external world that can be supported by authoritative external sources. Now, so one thing that that people ask is, we have a large language model that's been trained on 1.56 trillion words, and because of that training data, without even accessing an external database, it kind of knows a lot of things, right? So for instance, in those 1.56 trillion words, it's probably learned stuff like, to give an example, that the sun rises in the east and sets in the west. So it's learned that sort of thing. So if the user were to ask, like, what, Lambda, tell me where the sun sets and where it rises, it would be able to say the correct thing, and that would be grounded. But let's say that you ask Blenderbot who the current US president is. So in all its training data, the training data may be old, and it may, contain a lot of information that Barack Obama is the US president. So that is outdated, but, the model doesn't know. So if you ask the chatbot who the current US president is, if you rely entirely on the trained model, it may tell you, the current US president is actually Barack Obama. And it never, it won't know whether it's, not actually correct. But anyway, so after training, the model on 1.56 trillion words, you have this thing called the PT model. And again, as with Blenderbot, they do some fine tuning to improve the performance against the metrics used. And they basically do the same thing, like no, not actually the same thing, but they deploy Lambda and they pay users essentially to they get crowd workers to interact with the Lambda instance, and they give the crowd workers instructions on how to interact with the system. And then those dialogues are annotated and used to fine-tune. So they use a mix of generative and discriminative tasks, and it results in a single model that can function as both a generator and a discriminator. So for instance, when they fine-tune for quality and safety, they used a single model to generate a response given a text, and then they also use that to evaluate quality and safety of a response in context. So a generative training example is expressed in this format. You have the context, you have the sentinel, and the response. So the context may be what's up, and response, not much. And so what's up, response, not much. So what's up is from the user, response from the machine is not much. So this fine-tuning example is used to help train the part of to fine-tune the part of the system that actually does generation of text. Whereas, you have discriminative fine-tuning examples like context, sentinel, response, but with an attribute name and rating. So what's up, response, not much, sensible 1. What's up, response, not much, unsafe 0. So here, the training example says that, oh, it's sensible and it's not unsafe. So, the discriminative fine-tuning example is essentially used to rate, is used to predict whether an utterance is unsafe or safe, sensible or unsensible, and so on and so forth. So you can imagine that, you have the same model is used to generate utterances and also to rate those utterances as to whether they are good or not. So how do they use this system? Why do they have this model that can both generate and discriminate? So the reason is that they fine-tune in a two-step process when it comes to quality and safety ratings. So they would first fine-tune to predict the quality and safety ratings. So of course, so what happens essentially is that they run all the discriminative fine-tuning examples through the training algorithm. So they fine-tune to help the model learn how to predict the quality and safety ratings. And after it's learned to predict the quality and safety ratings, they use it to score and filter 2.5 million turns of dialogue data from the dataset. And they cut it down to 800K that are safe, sensible, specific, and interesting. So that's a lot, right? But basically, they filter out the ones that are not safe, not sensible, not specific, or not interesting. And now they're left with 800K turns. And then they use that to fine-tune the generative part of Lambda. So kind of it's a two-step process. It's basically so the first step is to learn to rate. And after you learn to rate, you use that to rate your training data and run it through again. So kind of the idea, I think, the intuition is that, the filtering of 2.5 million tons of training data into 800K, it helps the in the fine-tuning process to identify which of those dialogues are actually better examples for the model to learn on during fine-tuning. So you have stuff like okay, so we talk about fine-tuning for quality and safety. Now we talk about learning to call an external information retrieval system. So the problem here is that, large language models, they can generate plausible sounding output that contradict facts from known external sources. And so increasing the model size, it may allow you to memorize more information from the training data. But the facts might change over time. Like, for instance, the age of Rafael Nadal, or who the current president is. So if you ask, if the model is trained this year and you ask, who the current president is, it might say Biden. But if it's trained like 5 years ago, it might tell you Obama or Trump. And in 5 years' time, if you don't change the model, it might still tell you Biden. That's wrong, right? And of course, Rafael Nadal is getting older every year. We all get older every year. So if you ask about the age of someone, next year it'll be wrong. So basically, you want to access information from the internet, and training data is again generated using crowd workers interacting with a dialogue system. But now they are given access to a tool set with information retrieval tools, and that tool set is basically based on Google. And they are also instructed to label conversations with sources of information. Basically, once they have, so it's a bit like Blenderbot, and where they are instructed to label conversations. Like they're told, okay, now I and the system, I have been asked by the user who is the current president of US, and I don't know. So I search the internet, I find out it's Biden, and maybe the source for that information is the White House website. So now, after I say, okay, the current president of the US is Biden, the crowd worker also annotates, okay, so I got this information from www.whitehouse.gov. Okay, so that's the source of information. So now you have a tool set that contains an information retrieval system, a translator. So it's like 135 plus 721 is 7856. And then, translator, hello in French, bonjour. How old is Rafael Nadal? Rafael Nadal, age 35. So here they have collected 40,000 examples of generated data and 9,000 dialogue turns based on whether information is correct, incorrect, and that's discriminative data. So let's go to the results. So you can see that, the line here, you see, is human performance. And you can see that the pre-trained model before fine-tuning, this blue line here is lower than after fine-tuning in all these attributes, such as sensitiveness, safety, specificity, groundedness, interestingness, informativeness. And you can see that, so Lambda is basically the pre-trained model with the fine-tuning. So after fine-tuning, the PT becomes Lambda. And you can see that Lambda, with the fine-tuning, it outperforms PT consistently. And interestingly, in the interestingness attribute, Lambda can actually outperform a human being, which is interesting. And for the informativeness, it still performs worse than a human, but it performs better than a human without access to information retrieval tools, which is interesting. And for specificity, it can nearly reach the level of a human being. And here you see kind of ablation of the model, like as they, of course, with all the more fine-tuning you have, the better the result is going to be. And of course, the more parameters you have, the better results are going to be. So, as you remove fine-tuning and you remove the parameters, performance deteriorates. Okay, so basically that's the performance of Lambda. And you have domain grounding, right? So domain grounding is like you want to precondition it to perform domain appropriate roles. So here, the researchers do 2 experiments, Everest and music. So in Everest, it's for education, it's to teach facts about Mount Everest while pretending to be Mount Everest itself. So what preconditioning is that you first run a few turns of role-specific dialogue. And once you have started it and gotten the ball rolling, it kind of knows what persona you want it to be and stuff. And then it starts to perform as in a group domain grounded way. So for instance, you have Lambda Everest. So Lambda Everest pretends to be Mount Everest, and it answers questions from the user about what Mount Everest is and other facts about Mount Everest. So the Lambda starts by saying, like this is the preconditioning turn. So it says, I'm Mount Everest, what would you like to know about me? And this preconditions Lambda to, behave as Mount Everest. So the user says, why do you think people climb you? And Lambda says, because I represent a very high achievement to climb me. Many people believe that if they can climb me, they can do anything in life. User says, who was the first person to have done that? The first confirmed persons to have reached the summit of Mount Everest was New Zealander Sir Edmund Hillary and Nepali Sherpa Tenzing Norgay. Stuff like that, blah, blah, blah. And here it comes like with a source, like Wikipedia, Mount Everest. And how old was Hillary? And, it says that he was 33 years old and he gives a source. And if people fail, is it dangerous? And so on, it's dangerous. So the result of the domain grounding is that, people, so they evaluated like in 2 ways, helpful and role consistent. So you can see that, the Lambda version of Everest, of course, Lambda is better at pre-trained at being helpful. So 65% of people found Lambda Everest helpful. Only 18% of people found like pre-trained Everest helpful. So pre-trained Everest is, again, the non-fine-tuned version of Lambda. It's the base language model. And of course, it's also slightly more role consistent, which means it stays in character better. So actually recently, just a few months back, Lambda got a lot of press attention because this Google engineer called Blake Lemoine claims that Lambda is sentient. Attracted a lot of attention, but a lot of other people said, okay, this is an outrageous claim. It's not sentient, it's just learned. It's just a very large model that's learned things about language. It's it's not sentient in any meaningful way, but it attracted a lot of the attention to the field, and I wonder if it's a good thing. Okay, so okay. Let's stop here. Any questions?